Hi students, this is Mr. Yang. Today we are going to continue to learn more about vectors. In this lesson, we are going to do the opposite of addition. We are going to subtract vectors and also learn how to do scalar multiplication with vectors. But before we do that, let's review something we have learned about matrix. How did we multiply matrix with scalar? All we did was just multiplying the number outside, which is the scalar, into the matrix, into every single number inside matrix. So A would just give you -3, 0, 6, 15, 12, and 9. And B would just give you a -14, a 2, and a -6. For part C, that's something we have learned in the last lesson. Vector is a quantity that measures magnitude and direction. Then, what do you think a negative vector A would represent? It would actually represent A, but the negative sign indicated is actually going to the opposite direction. And that's kind of how subtraction will work. Now let's get to today's lesson. Subtract vectors. Subtracting a vector is the same as adding its opposite. A minus B is the same as A plus a negative B, which kind of work the same way as a number. If you ever have like a 3 minus 4, it's the same as a 3 plus a -4. Vector works the same way. This is just the additive inverse property applied to vectors. Vector B plus negative vector B equals 0. An opposite vector has the same magnitude, but in the opposite direction. So that means when you have a negative vector and that you're trying to draw based on a vector given, they will just form a line. Remember, the resultant vector goes from the tail of the first vector to the tip of the second vector. And you'll see what that means when we get to some diagrams. First, negative vector B. Vector B is pointing to the upper right, and negative B would be pointing to the down left. And you can clearly see they will form a line. Now the tail to tip method, let's say our B is over here, we're going to need to do A minus B, so we need to draw where negative B is. And in that case, the whole thing is changed into an A plus a negative B. And the tail and the tip are connected, as you can see. And of course, that's what this resultant vector is talking about. It's got to be from the tail of the first vector to the tip of the second vector. So this would be the vector A minus vector B. Parallelogram, it still works the same way. We are going to move the negative B down to the same tail, same starting point. So we can actually form the parallelogram and then the diagonal from the same starting point to the same ending point. That would give us the A minus B. Now let's see some examples. Example 1. Draw the resultant vector for vector A minus vector B. Vector B is pointing to the right overall. So I am going to need to stay on the same line, but pointing exactly to the left, about the same length. So negative B. To be more precise, you are supposed to measure them, but for example purpose, we're just going to, do an estimation. Now the whole thing becomes A plus a negative vector B. So the tail is right here, the tip is right here. That means this portion would represent my A minus B. That is example 1. Example 2. A is something we have already learned in the last lesson. All we need to do is add the horizontal components and add the vertical component. So this is going to give us a -17 plus a -3, 18 plus a -2, which is going to be a -20 and a 16. Then U minus V, of course, that means we're subtracting -17 minus -3. Something I've emphasized on before, when you subtract a negative number, you are going to need to have two negative signs. We have 18 minus a -2. That becomes plus, so we are going to have a -14 and a +20. B plus U, well, this is supposed to be the same as A. Let's try it. Let's find out. -3 minus 7 minus, plus -17. -2 plus 18, that is -20, 16. Yep, they are the same because addition for vectors is commutative. That's something we have learned in the last lesson. Lastly, V minus VU. Of course, you need to do it in this order. So -3 minus -17, -2 minus 18, that is going to give you a +14 and a -20. Even though the numbers look similar to B, they are opposite numbers, so that they are not the same. That means subtraction is not commutative. Now example 3. My U is right here, 5 negative 4. So I can draw 5, negative 4. That is my u. My v is 6, negative 2, which is right here. That is my v. But the question is asking you to draw u minus v. So I need my negative v. Since v is right 6 down 2, I need left 6 and up 2. So that would be my negative v. Now I have them starting from the same initial point, so I need to form my parallelogram. The u is right 5 down 4, so right 5 down 4 is going to be here. And then, of course, this would be my negative v again. So that's my negative v, and this is my u. Then, of course, I need to start from the same point and end at the same point. This would be my resultant, which is u plus negative v, or just u minus v. So this is my graphing. We're using the parallelogram method. Now let's actually check with the components. So if we want to do u minus v, that is going to be, well, let me rewrite that v. That is going to be 5 minus 6, and pointy brackets, negative 4 minus negative 2. That will give us a negative 1, negative 2. And as you can see in the diagram, well, it is going left 1, down 2, so that is u minus v. As for the magnitude, u minus v, that is going to be negative 1 squared plus negative 2 squared, which is 1 plus 4, which is square root of 5. That is example 3. Moving on. And that is actually everything for subtraction, because subtraction is just addition. It's just we're adding the opposite of what's given. Now, moving on, scalar multiplication. A vector can be multiplied by a scalar. Multiplying a vector by a scalar changes the magnitude of the vector, but does not change its direction. So in comparison with subtraction, or in comparison with opposite, that one would actually keep the same magnitude but change the direction. This time we're changing the magnitude but keep the direction for multiplication. So on the left side, you are given a vector v, twice a vector v, and a half of vector v. In comparison with the w and x and z on the right side, you may notice these are all pointing to the same direction, but this is pointing to the complete opposite direction. And in that case, well, this is kind of how scalar would work. When you need to do it twice, well, you can see the length is clearly twice as long. And another thing is, when we say it does not change its direction, is when we actually multiply by a scalar that is positive. Of course, when you do negative, that is suddenly becoming subtraction, not just a scalar multiplication. So now let's have a look. Multiplying by a vector by a negative number reverses the direction of the vector. The multiplication of the scalar k and the vector v is called scalar multiplication, and we write this product as k times v, just like when you do like 2x, number in the front with a variable. So example 4. Given these vectors, let's graph the resultant and label the resultant. So first, v. We do need to kind of know how to describe the direction when we are given a vector. But of course, a vector has a horizontal component and a vertical component. So we are going to use these to discuss our directions. So you will notice it's actually the same as when we talk about slopes. So to talk about the direction of this given vector, that is to the right 3 and up 2. So right 3, up 2. But I need 3 times of that, then of course I need to go to the right 9 and up 6. Because that's kind of how it works. We are going to extend the horizontal portion and the vertical portion. So 9, 6. That means my resultant is going to be right here. And of course, they should coincide because they are pointing to the same direction, just different magnitude. In that case, that is my 3 of my vector v. Next, 1/2 vector w. Initial point is not at the origin anymore. Well, then we are just going to start counting from the initial point. It is going to the left by 10, and then it is going up by 8. But I need a half of it, so of course that means I need to go to the left by 5 and then up 4. So left 5, up 4 is going to be right here. So this is my 1/2 vector w. However, that's not the only way to draw it, because as of right now, it is not in standard position. You can, of course, choose to draw it in the standard position, which means we will start from 0, 0, and then left 5, up 4. So this could also be our 1/2 vector W. That kind of shows the feature, something special about vector. You can move it anywhere in the plane. It will still represent the same vector if they have the same magnitude and point to the same direction. Now let's move on to C. This time is -1/3, so let's look at our U first. That is going to the right by 6, and then it's going down by 9. But I need -1/3 of it. That means I need to go to the opposite direction and then 1/3 of it. So in that case, it's going to be left 2, it's going to be left 2, and then up 3. So left 2, up 3 right here. And as you may notice, even though that is a negative vector and Siemens numbers are different because they're different sizes, they are still going to be on the same line, because that's kind of how direction works. Even if it's opposite, it's a direct opposite direction. Next, 2s. Let's actually this time draw it as a standard position, standard form. So 2s right now is going up 1, right 3. So I need up 2, right 6. And that means I can draw my 2s starting from the origin right there. That is D. The only things that are important about vector are its magnitude and direction. It doesn't matter where it is on the plane. That is something we have mentioned last time, and that is why in the previous example, I did draw them in different places. Some in standard positions, some just have the same initial point. You can move a vector around whenever you want or need it to be, and it will still be the same vector. Scalar multiplication in component form is even easier. It's like distributing a scale factor through the brackets. So just like what we did with the prior knowledge for a matrix, this is the same. All you need to do is look at the number in the front, give it to all the components inside the vector. And that's it. And lastly, of course, we need to talk about the magnitude. The vector C times V has a magnitude of, this is something that's different, that's special, that I need to emphasize on. It's not just the number C in the front. When you talk about magnitude, because we can have negative magnitude, we got to make sure the whole thing will come out to be a positive. That is why we are going to put absolute value around that C, then multiply with the magnitude of V. The vector CV has a direction that is the same as the direction of V if C is greater than 0. Of course, when it's positive, it's going to keep the same direction. But when it's negative, it is going to the direct opposite direction. Now let's have a look at an example. Example 5. First, let's find these scalar multiplication resultant. -3w, all I need to do is multiply everything by a -3. That would give me a +6 and a -24. For C, my B is 5, 4, so that is going to be a 20 and a 16. My B is going to be -2 times everything, so -10, -8. And lastly, for D, 1/4 times that, so that is going to give me a -1/2 and a 2. The 2 times V is going to give me a 10 and 8. As you may notice, you can either choose to keep the -2 together with the numbers, then change the middle into a plus, or you can keep the negative sign and just multiply the numbers. So now I'm still doing subtraction. -1/2 minus 10 is -21 over 2. Then 2 minus 8 is a -6. That is D. Moving on, E and F. Compare the magnitude of 4b and -3b. Let's calculate it out. We already have 4b right here. So the magnitude of 4b is going to be the square root of 20 squared plus 16 squared. That is going to give us a square root of 656. I'm going to do the factory right here. 656 is a 2. We got a 328. Another 2, we got a 164. Another 2, we got 82. Another 2, we got 41. At 41, you can't keep going any further. That is actually a prime number. That means we have 1, 2, 3, 4 2s, or in other words, 2 pairs of 2. That means we can take out a pair of 2. We can take out 2 2s and leave a 41 inside. That is the magnitude for 4b. Moving on, let's find magnitude of negative 3v now. We don't have that calculated out yet, so we're just going to multiply everything to inside v by a negative 3, which gives us negative 15 and negative 12. So negative 3 v is going to give us square root of negative 15 squared plus negative 12 squared. That is 369. So 369. That's not an even number, so we can't divide it by a 2. But you may notice 3, 6, and 9 are all divisible by a 3. I'm just going to start with a 3. That's going to leave me with a 1, 2, 3. Take out another 3. We are going to have a 41. That means we have a pair of 3 and a 41. So take out the pair, which is a 3. Leave the 41. Now with these two, you may see they both have the square root of 41. Then if you actually test it out, square root of 41 is the magnitude of v. So in order to find 4v, we could have just used the v multiplied by a 4. That's how it works. As for the negative 3v, we could have used a v, but not multiplied by a negative 3, since we can't have a we can't have a negative magnitude. That's why we got to change it into a positive 3. That's kind of some comparison between these two. As for the direction, of course, they are opposite directions. You see, these are all positive, these are all negative, then of course they're going to the opposite directions. Moving on, the very last example. Let's calculate the magnitude for v first. Negative 3 squared plus 4 squared, that is square root of 25, which is a 5. 6v, that's 6 times the v given v, which is negative 18, 24. And then we have negative 3 multiplied with negative 3, 12. That is going to be a 9 and a negative 12. Now it's time to calculate the magnitude for 6v. We have it right here. That is going to be negative 18 squared plus 24 squared, 324 and 570. 6 is going to add together to be a 900 under the square root, which could be simplified as a 30. Lastly, 9 and negative 12. So 9 squared plus negative 12 squared, and that is going to be 81 and 144, so 225 under the root, which is going to give us a 15. But of course, that is not the fastest way. We have just learned that we can choose to just use v and the number. So this, we can use the 5. That's the same as 6 times the magnitude of v, which is 5. So 6 times 5, that's 30. That's a lot faster. Or we can do this. So use the 5. That means I can change it into a positive 3, multiply with the vector v. That is going to be 3 times the v1 is 5. So we got 15. Still the same answer, but it is a lot faster. And that means we can, again, relate the magnitude of just a v with whatever number is in the front and just do it that way. That is the last example, which concludes this lesson about subtracting vectors and scalar multiplication. Thank you.